So chapter 16 is on aldehydes and ketones. And really the key here is what these two functional groups have in common. And that's called the carbonyl group. So it's a carbon double bonded to an oxygen. So the carbonyl is that C double bond O. And so it's going to be in chapter 16, which we're doing, like I said, for the next 3 class periods. It is also the key in chapter 17, so we're going to continue to talk about that. And then it's also in chapters 18 and 19. So like I said, you know, this is a biggie, so that's why we're going to spend a good bit of time in this introductory chapter. And then, like I said, as we go on, the next 3 chapters will also build on reactions at this carbonyl. Again, a C double bonded now to an O, right? So we've seen C double bonded C, but now what happens when we have that O, right, as part of that double bond? And so the carbonyl has 1 sigma bond, right, and 1 pi bond. And so since it's a double bond, it is considered to be sp2 hybridized. So just a couple of drawings here, some molecular orbital for the 2 bonds. So again, you'll have that carbon, right, oxygen bond. So of course, remember that you have those lone pairs. So this looks different than a carbon-carbon double bond because carbon doesn't have any lone pairs, right? All of the electrons in carbon, valence electrons, are participating in a bond, but oxygen has those 2, right, lone pairs. So again, that, right, forms, right, that potential for a dipole. So we'll talk about that as well, but it's a carbon, right, double bonded to the oxygen here. So the 2 first functional groups that contain the carbonyl are the aldehyde and ketones. So what makes them different from each other? So the aldehyde has the carbonyl and an H attached. Okay, so when you look at some structures, you can see the carbon, right, with the carbonyl, and then an H. Carbon of the carbonyl, and then an H. Does that make sense? So that's an aldehyde. The ketone has 2 carbons attached to the carbonyl. So if we go down here, right, the carbonyl, and then 2 carbons, 1 on each side. And again, it will be a chain of carbons. It's not just necessarily 1 carbon on each side, but a carbon chain, right? So, but the aldehyde has to have an H, right? So it can be a carbon chain on this side, but there has to be an H attached in order to be an aldehyde. So of course, we're still using for naming, right? Methyl, ethyl, propyl, butyl, I mean, all those prefixes that we've been learning since last semester. So 1 carbon is meth, so methanal. So Al is the suffix associated with an aldehyde. So 2 carbons is ethanal, right? Ethanal. And then ketone, the smallest ketone has 3 carbons, right? Because you have to have the carbon of the carbonyl and then at least 1 carbon on each side. So the smallest ketone is propanol, which happens to be acetone. So the common name, right, and I'm pretty sure everybody's used acetone. I know we use it in the lab too, so, but it's a nail polish remover and things, solvents that we use at home as well. So these are, again, just in general. So just to refresh our memories on the naming, right, we're going to look for the parent chain, which is the longest chain containing your carbonyl. Again, the aldehyde, the suffix is al, so we drop the E at al, right? Remember that you still can have a double bond or a triple bond in the chain. So an AN means, right, that there's single bonds, but it could be switched to the EN if there was a double bond, or YN if there was a triple bond. So that's called the infix. And then, of course, right, you would number where those double bonds were. If it's cyclic, then the aldehyde has to come off of the cycle. There's not enough bonds for the aldehyde to participate in the cycle. And so in order to take care of that carbon that's going to be on the outside, it's called Carbaldehyde. So if it's cyclic, okay, it gets a different suffix than when it's linear. And that's because the carbon of the aldehyde group has to be outside of the ring. Okay, so again, for the aldehydes here, right, remember that the carbonyl is now the highest priority group, so that has to be carbon number 1. And with the aldehyde, because it has an H associated with the functional group, it always has to be at the terminal, at the ends of the chain. So it is always going to be carbon 1. So 1, 2, 3, right, and 4. So 3-methyl-butanol, right, rather than counting from this side. We have to start where the carbonyl is, right? So here it is again. So 1, 2, 3, right? So the double bond is at carbon 2, so 2-propanol. Does that make sense? So, and then here I have 2 double bonds, one at 2 and one at 6. Is that right? Yeah. And then you also have a methyl, right? 2 methyls, excuse me, at 3 and 7, right? So 3,7-dimethyl, 2,6-octadienol, right? So diene, because you have 2 double bonds. And then, of course, it's at carbon 2, this double bond is E. So that's where you see the 2E, 3,7-dimethyl, 2,6-octadienol, right? So that's a geraniol, which is a naturally occurring molecule. Yep.
Why are these
on opposite sides?
Huh?
Oh, okay. Yeah.
Yeah, so this one can't be E or Z because these two, right, are the same. So we can't tell which one, right? We can't tell them apart, so we can't do it. But this one you have, right, the larger group versus, right, the large group on opposite sides. So that's E. If they were on the same side, they would be Z. Now, like I said, the cyclic, because if I tried to put a double bond and an H, that would be too many bonds, right? That would be 5. The aldehyde group, the C double bond OH, has to be outside of the ring. So that's cyclopentane carbaldehyde. So carbaldehyde, the carbon has to be expressed that's outside of the ring. So it gets a different suffix here. Okay, same thing here, right? So this is going to be hydroxycyclohexane here. And then the carbaldehyde for the group on the outside. And then, of course, it's trans, right? Because you have a wedge and a dash.
So you don't have to put 1 because it's already known.
It's always 1, yeah, good point. So you've noticed that the aldehyde, I'm not putting 1 out, 1 out, 1 out, right? Because it's always 1. It has to be at the end of the chain. So, but you could, if you put it in, I wouldn't penalize, but that's why you don't see it. Thank you for reminding me at that point. Yeah. Okay, and then again with the benzene, same thing, right? The aldehyde is outside, so together we call it benzaldehyde. That's actually a common name, but IUPAC accepts this as the IUPAC as well. Okay, and then this is cinnamaldehyde, so it's what we have in cinnamon that makes it smell and taste like it does. So, and that's trans 3-phenyl 2-propanol. So you can see it there. So just some, again, review of the naming for aldehydes. Any other questions on this? Make sense? Again, this is one of the ones you'll want to know for the next exam. And then the other one is ketones. So now again, the ketone has 2 carbons, so no hydrogens now. Okay, so the 2 carbons, the smallest then has to be 3, right? The carbonyl plus 1 carbon on each side, so that's propanol. Okay, but we're still looking longest chain containing the carbonyl. Now the E drops, it becomes -one. Right, and then you want to give the carbonyl the smallest number possible. Now it's going to be in the middle of the chain somewhere, so you do want to locate it where it is. So this should actually be 2-propanol, right, if you were putting in the locator. Does that make sense? Right, this is 1, 2, 3, right, with this phenyl coming out, right? But this is acetylphenol, which again is a common name that IUPAC accepts. And then this is benzophenone, so 2 of them together, right? And then this is 1-phenyl, right, pentanone, and now this is carbon 1, so 1-pentanone. So for the ketones, you do have to locate where the double bond O is. Okay, of course, except the common names here. Right, so if this wasn't common name, what would we call it? 1, 2, and then this is coming off, right, of that carbon 1. This would be 1 phenyl, 1 ethanol. Does that make sense? So if you were doing IUPAC, you could do it, but acetophenone is acceptable by IUPAC, so you're welcome to remember that, right? But there's 2 carbons, would you agree, in the chain, right? And then this is a substituent, right, phenyl. And then this is carbon 1, because it's where the carbonyl is, 1, 2. So this is 1 phenyl, 1 acetyl, or ethanol, right, or acetone, excuse me. So you could do IUPAC on those if you wanted. What would this one be called?
One diphenyl.
Yeah, diphenyl, right? You have 2 of them, right? It's actually 1,1 diphenyl. So again, it's kind of confusing. So IUPAC has decided to accept, right, the common names, and just a few to remember. I think they're worth knowing, but so just keep in mind that those are acceptable. All right, now I told you that the carbonyl so far is the highest priority, okay? But we are coming on next chapter, carboxylic acids, and carboxylic acid is the highest priority, okay? So we haven't done that yet, so right now the carbonyl is it, but it's gonna be the carboxylic acid by the time we get to next chapter. And what that means then is if you have one of the other functional groups, right, so if you have carboxylic acid, right, that's what COOH here, not the last one, but these 4, right? If you have another functional group, in this case an aldehyde, that becomes a substituent name or a lower priority name. And oxo is for the carbonyl. Hydroxy is for the alcohol. Amino is for when you have the nitrogen. Okay, and then thiol becomes mercapto. So we do want to keep in mind that you may see compounds with multiple functional groups. So it is important that you know, right, these lower priority the prefixes for that. So, or you know, I like to call them substituent names if you have to give those as substituents. So, and again, so far aldehydes, then ketones, then alcohols, aminos, sulfurhydrous. We have done all of those, but carboxylic acids will do it next chapter. So, and that is the highest priority there. So you just want to keep those in mind. And of course, common names, some others that are acceptable. So for 1 carbon, yes, that's methanol. But usually we use the name formaldehyde, and you've probably heard of this name, right? Formaldehyde is embalming fluid, also used for preserving tissue. So maybe in biology class you've seen, you know, things in bottles in a liquid, right? Ominous looking. So that's formaldehyde is the liquid, and that's actually formalin, excuse me, which is 37% formaldehyde in water, because formaldehyde is a gas. So 37% in water makes the solution that we use as embalming fluid. So, but formaldehyde is accepted, and together with that is formic acid. So 1 carbon as an aldehyde, 1 carbon as a carboxylic acid. They get that same prefix there. Form is for 1 carbon. Acet, A-C-E-T, is for 2 carbons. So acetaldehyde, also again acetic acid. So acetic acid, you know, is in vinegar. So that's some acceptable names there for aldehydes, and some carboxylic acids as well. And again, we'll touch on that in the next chapter, bless you. For the ketones, though, what you do is you take the carbonyl, you name that ketone, and then you name both sides, like we did with the esters, remember that? So this side is 2 carbons, so that's ethyl, right? This side is isopropyl. So again, alphabetical order, so it becomes ethyl isopropyl ketone, right? If you have 2 that are the same, they're both ethyls, then it becomes diethyl ketone. Does that make sense? 2, right, cyclohexanes, so again, dicyclohexoketone. Makes sense? So you're welcome again, either way you want a name on the exam is acceptable, just, you know, as long as it's correct. So if you want to use the common name, you're welcome to do so. So for aldehydes and ketones. So that's naming. Any questions on naming? All right. So then to the properties, again, because you now have, right, an oxygen associated with this functional group, you have the potential for a dipole. So remember that N, O, or F are the most electronegative atoms on the periodic table. So they're really going to want to pull the electrons towards it. So when it does, then carbon becomes partially positive. So you have that negative positive, right, polarity there, which we call a dipole. Okay, so and you also have the potential of having resonance structures, contributing resonance structures. So remember that that always leads to stabilizing, right? So whenever you have an ion, so that's going to be very important in chapters, I guess chapter 19, when we talk about those as ions. But again, that polarity is really the key here. You're going to have a dipole between the carbon and the oxygen. So that's totally different than having a carbon double bonded to another carbon, right? That's going to be a non-polar kind of interaction. There's no difference in electronegativity. So both aldehydes and ketones, they're going to be able to participate in dipole-dipole interaction, right? But would you agree they cannot hydrogen bond, right? There's actually no hydrogen associated with the oxygen. And so, yes, that's going to be, the dipole interaction will help with boiling points, but is it going to be as high boiling points as something like an alcohol? No, right? Because alcohols can't hydrogen bond. Does that make sense? So yes, it's going to be higher than an alkane, but it's not going to be as high as an alcohol. So we usually think of aldehydes and ketones as intermediate between alcohols and alkanes, okay? Because it is higher because of the dipole-dipole interaction, but it's not as high as something like a hydrogen bond. Okay, so that makes sense there. So I just put this is not in your notes, but this came from chapter 10 at the very beginning, first day that we touched on this. Like, how many reactions do we know so far?
There's 5. Acid, catalyzed.
Right, so acid.
Base, catalyzed.
Yeah.
Substitute.
Well, I don't know what order I did.
Redox,
Redox, right? Then addition, right? Substitution, right? And then eliminations, right? So those were the 5 that, again, we've been really, they've come up over and over again, right? As we've been learning these new functional groups. So there hasn't really been any new reactions so far. We've just stayed to the 5 that we touched on the very first day, okay? Now, today, we're going to go for something new. Now, it is on this list already. It's called addition. Okay, but do you remember what kind of addition it was in chapter 6, or what kind of group gets added, or what kind of addition that's called what? Do you remember?
Halogenation.
Not halogenation. Even though halogen can be added, but those are usually called electrophilic. Now, why are they called electrophilic? Electrophilic is an atom that wants electrons. So what wants the electrons in an alkene situation?
When you break that double bond.
Yeah, when you break that double bond, what do you form?
Carbocation.
It's carbocation, right? So with the alkenes, right, what's going to happen is you're going to end up with, right, you add, let's say an H, right, just to start, the other carbon becomes what we call an electrophile. So these are called electrophilic, additions, right? Electrophilic additions. Does that make sense? And we have also talked about nucleophilic substitutions, right? Where we have, right, a nucleophile, right, which is going to attack, right, and in this case you have a leaving group, it's going to attack the carbon, the leaving group leaves, right? And now you've substituted, right, your new carbon, right, and then you get the leaving group as an ion, right? So we've done electrophilic addition, and we've done, right, nucleophilic substitution. Guess what we're going to do today? Mishmash the two together. And we're going to do nucleophilic addition. Okay? So that's the new reaction. So technically it's still in there, it's addition. But the addition we did previous to this is different. It was called electrophilic addition because we had a carbocation. We're not going to have a carbocation here. We're going to have a nucleophile attacking, Okay, so that's nucleophilic. Does that make sense? And what has to happen then is that the double bond, the pi, right, that pi bond is going to have to open. So kind of like the epoxide, remember that in the epoxide, yeah, you open the ring, right, and that breaks a bond, right? So the leaving group is actually attached already to the carbon. It's kind of a similar thing. The O is already attached, right, by a sigma bond, and what I need to do is open the pi bond so that carbon then has 4 bonds, right? Instead of just having 3 groups, now I have 4 groups. So would you agree that I went from trigonoplanar to tetrahedral, right? That makes sense? I went from sp2 to sp3. Does that make sense? So the key here is, right, a nucleophile is going to initiate this whole process, right? The nucleophile is going to attack. But then something has to happen at the carbonyl, and that's breaking of the pi bond. The sigma remains, right, the single bond. But by breaking the pi bond, you make room for a new, right, an addition of the nucleophile. Does that make sense? Why this is a different kind of reaction. It's totally different than an electrophilic addition, right? So this is now a nucleophilic addition. Does that make sense? So this is the theme, and it's going to be the theme this chapter. It's going to be the theme next chapter, the chapter after, and the following chapter, right? So we really, again, want to spend time really getting used to this, because once you get used to, okay, the nucleophile attacks, the double bond opens, right? That's going to happen over and over and over and over again. So what are you going to have to determine? The only thing you have to determine, the nucleophile is, right? Does that make sense? So if we can, right, get a hang of this theme, right? I like to call them reaction themes because they keep showing up and showing up and showing up. So it's not like you're learning 100 reactions. You're just learning what to add. Right? If you can do that, this becomes really much simpler, I promise. Does that make sense? So this is an addition, but it's a, right, nucleophilic addition. And the product, like I said, is always going to be a new carbon, now with 4 bonds. So it's called a tetrahedral carbonyl addition compound. I know it's a mouthful. So it's TCA. I think it's TCAI is what they name it later because it's called an intermediate. So, but it gives you always that, right, tetrahedral carbon, 4 things instead of 3 things, right? You started with 3 things attached. When the nucleophile adds, you then end up with 4 things. Does that make sense? So again, this is a theme, and it's going to come back for the next 4 chapters. So we really, you know, the more familiar we become with this, I think the better we're going to be at learning these reactions. Okay? Does that make sense so far? So again, an addition, but a little bit different addition. The second theme is something I just want to bring back up because we've been talking about this since, again, alcohols, that you have this protonation step that always initiates the process. So what is the protonation in this case? We're going to protonate the oxygen of the carbonyl. Okay, so you can see that the oxygen of the carbonyl, right, picks up a hydrogen, so it becomes protonated, right? Positive charge on there because oxygen has 1 more bond than what it wants, which is going to mean that it's going to want to shift things around. Okay, and when it does, it's going to end up with a single bond O. Does that make sense? So it gives a boost to this reaction. Okay, so you're always going to start with a protonation, which again we saw it with the alcohol, but the purpose with the alcohol was to form the leaving group. Here you're not really forming the leaving group, but you are giving the carbonyl more incentive to break the pi bond. So you're still giving it, right, that power, and so we call that, right, making it more reactive, the power to open that bond, and then the nucleophile can come, right, attack, and the double bond will will open very easily. So this is also involved here. And again, the first step, right, is fast, the protonation. What's going to be slow and rate determining is still going to be the nucleophilic attack. So this is still the significant step on here. But with the protonation, we're making it, okay, a little bit easier to do, more reactive, making the group more reactive. Because carbonyls, they're pretty stable, so we have to take that into consideration, so having that double bond out. Okay, and the next thing I want to touch on is stereochemistry. So we are going from something that is planar, right, trigonal planar, 3 groups, right, which means that the molecule is flat. Okay, and now we are going to go to a molecule that is tetrahedral, which is 3D. So we have to figure out, right, what's going to happen when that nucleophile attack. And this we covered back in chapter 3 of last semester. So this, again, is not new, but I'm just trying to bring it back up to show you, okay? We already know all this stuff. We just have to put it all together to figure out the reactions in this chapter. So remember with the planar, right, that means that if the nucleophile comes in, it can attack over here, or it can attack over here, right? There's no preference between either side. Remember that from chapter 3? And so what happens when there is no preference? You end up with 50-50, right, of R and S, which is called a racemic. Remember that? So again, this is not new, but it's going to be very important when you're drawing the products of these reactions, because you are starting with a planar molecule. That carbonyl is planar. So the nucleophile is going to attack, right, from both sides, both faces, as it's shown here, which means the product is not going to be just one, right, but 2 stereoisomers, an R and an S. Does that make sense? So that is always, again, something that occurs. So on Al, it's going to require you to, always be thinking, should I do just 1 canvas or 2 canvases, right? For these reactions, a lot of times you're going to have to draw both R and S. Okay, but remember, it's really easy. Once you draw on one, how do you make the other? You just flip 2, right? So it's not like you have to go back and do any, additional work. You just want to make sure you do the first one correctly, and then you flip, right? The wedge and the dash. Bless you. Okay, but just flip 2. Don't flip all 4. Then you make the same molecule again. Okay? So you are creating that chiral center. Okay, so you do, again, want to, right, reinforcement here of this theme, which again is not new. We learned a while back. I know it's now been a while, but it's something you want to consider strongly when you're doing this. Okay. All right, so with this in mind, right, knowing that, okay, the nucleophile is going to come in, it's going to attack my carbon of the carbonyl, opening the double bond, right, that's the theme there. There's a potential for you to use those carbanions that we discussed previously. So we just spent a good bit of time, right, on chapter 15, talking about those organometallics. So organometallics couple very nicely with carbonyl. So this is a very good combination. So if you're trying to add carbons to your chain, use them. They're very, very useful. Remember that R group can be 1 carbon, can be 10 carbons, can be a cyclic, can be a benzene. I mean, you can add just about anything carbon-based, right? Okay. Now you can also, if you are wanting to add just 2 carbons, you can also use the alkyne. Right? If you're trying to add carbon and then be able to convert the nitrogen, right, into maybe an amine or some other groups that we're going to get into as we go into the next 3 chapters here. So this is the cyanide. You can also do that. Does that make sense? So you're trying, here the purpose is to add these new carbon bonds. So that's really the key. Okay? And they work very well with carbonyls, in particular the organometallics, the Grignard, okay, and the organolithiums. Remember the Gilmans, right? So we talked about a number of these in chapter 15, last chapter. Okay, so this is going to be something we'll see a lot here. So let's start with the green yard. So remember again that the green yard is carbon magnesium, right? And then you're going to have a halide associated with that to stabilize the magnesium, right? Because magnesium is M2+, so the carbon is one bond, and then the halide is going to be that second bond, okay? So that the magnesium is neutral. And then what's going to happen is magnesium tends to be positive, which is going to allow the carbon to become negative, which that's what we call that carbanion, right? And the carbanion is going to serve as our nucleophile. So again, when you see green yard, you should think the nucleophile as carbanion. Does that make sense? So that's really what you're trying to figure out. When you're learning all of these additions that we're about to learn, what is going to be added? So when I have a green yard, what I'm going to add is carbons, right? 1 carbon, 10 carbons, a cyclic, a benzene, I mean, you name it, whatever that R group is of the green yard, which can be just about anything, but it's going to be a carbon chain, right? Does that make sense? What the nucleophile is, right? So the nucleophile is the carbanion. It's going to bear the negative charge, just like we would like to see, right? This is the ideal form of a nucleophile with the electrons and a negative charge. That's good nucleophile, right? We want a good nucleophile to do these reactions, okay? Does that make sense? So, question? Or just... All right. Okay, so this is just showing you again, right, an example of that. So we're going to use formaldehyde, okay, as our carbonyl, okay, and then we're, again, green yard. So what's, right, I look at this and I should see what? This, right? This is what's going to be added to my carbon, right? To form my tetrahedral carbon. Does that make sense? So when I look at this, my eye should say, yes, that carbon is going to be doing the attacking here, right? And it's going to take with it the other carbons, right? Whatever is attached. Does that make sense? So the new bond is going to be between this CH2 and the carbon of the carbonyl. Of course, that means the pi, right, bond is going to have to break. Because there's, right, has to only, carbon can only have 4 bonds, so something's going to have to give, and it's the pi bond. So that leaves you with that ion, right, oxygen, 1 too many pairs of electrons. So we just add a weak acid, HCl in water, to add the hydrogen, which then makes an alcohol as my product. But of course, this alcohol has the 2 carbons of my nucleophile, right? So really, this is the nucleophile, right? This came from the original carbonyl. Does that make sense? Right? Because that's really, once you can, you know, do this, and I saw in the exam, a lot of people, you knew it should be a nucleophilic reaction, but you could not come up with a nucleophile because you just wrote nucleophile or N, you know, like this. And I'm like, that's not good enough, right? You've got to be able to figure out what the nucleophile is. Does that make sense? So I could tell, again, I know you studied, that you prepared, but you're not quite there. So you have to, you know, make it up that hump there. And now I think if you can figure out what the nucleophile should be in these reactions, it's going to be really helpful. Okay? And because the formaldehyde, right, the carbon is at the end of the chain because it has the hydrogen, that's always going to give you an alcohol that's going to be on the first carbon. So we call those primary alcohols. Now let's say that the carbonyl is a ketone. Or I'm sorry, that was formaldehyde. Formaldehyde has 2 hydrogens. Excuse me. Let me go back here. So formaldehyde is the only aldehyde that has 2 hydrogens. So when it attacks, it only really adds the carbon at the end, so it always makes it primary. But let's say we have another aldehyde, any other aldehyde. So in this case, this is acetaldehyde, so now I have 2 carbons, right? So again, when I look at this, what's my nucleophile?
The cyclohexane.
The cyclohexane, right? So the carbon of the cyclohexane is going to be the one attacking my carbonyl. My pi bond is going to hold it, right? And so now you have, right, the product salt, and then you add weak acid, makes it an alcohol. Does that make sense? It's always the same process. But now, right, you had a hydrogen here, which is not drawn, but you had another carbon. So now your alcohol is next to 2 carbons, which makes it secondary. So formaldehyde always gives you primary. Any other aldehyde is going to give you secondary. And what happens if we use a ketone? There's already going to be how many carbons?
2.
2. So you're going to add another carbon, so that's going to make it tertiary. Does that make sense? But again, we look at this, what's my nucleophile? Phenyl, a benzene right now. Does that make sense? It's just abbreviated pH, but it's a benzene. Right? And so if the benzene attacks, right, opens the pi bond, you now have a new bond, right? The salt, you add a weak acid, and you make your alcohol, which is now 1, 2, 3 carbons attached, which is tertiary. So a ketone always makes a tertiary alcohol as a product. Yeah.
Would there ever be rearrangement? Where that would it?
It does not. You don't have a carbon cation. Carbocations lead to rearrangements. You never form the ion because the nucleophilic attack is at the same time as the pi bond opening. Does that make sense? So there is no rearrangement. Yeah? Good question though. Did everybody catch that? He was asking, would there be a possibility of rearranging these carbons? And because you never form the positive charge on the carbon, right? Even though there's a resonance where there is a charge, that doesn't usually participate in the reaction. So no, there is no rearrangement. What you see is what you get as a product, okay? So formaldehyde gives you primary, aldehydes, any other, gives you secondary, and ketones always give you tertiary alcohol. So the product is an alcohol. Does that make sense? How these work with the green yards? All right, so let's practice here. So this is my product, 2-phenyl, 2-butanol. Okay, it was synthesized by combination of a green yard and a ketone. Okay, and there's 3 possible combinations, and I want you to give me the 3 possible combinations. Does that make sense? So you should have a green yard and a ketone, and there should be 3 different combinations that you can use to get the same product. So take some time to see if you understand what is my nucleophile. I'm telling you that there was a potential of 3 different nucleophiles to form this product. What are they? Yes, I want you to find all 3. So look at this product. This is the product. And there are 3 combinations. So try to figure out what 3 nucleophiles I could have used. Remember, what's the nucleophile in a green yard? The carbon, right? So that R, MGBR, right? Does that make sense? Plus the ketone, right? So there's another R1, R2, right? And R3. So I'm trying to figure out how can I make combinations out of this? Right? Three combinations.
Are you sure?
Oh, no, you're feeling hunted. You're trying to.
Tell me the truth. So these 3 have that. These 2 and that 2. They have that as well. Perfect. Does that make sense though?
It does.
It does, right? Anybody else feel like they got it?
Almost.
CH3.
I think that's what you meant. Okay. Perfect. Does that make sense though? think, well, what did you guys think was the key? The two that I said got it right. What do you think was the key figuring out what?
You just look at the center carbon.
Yeah,
That's
right? The
attached.
carbon with the OH has to have been part of the carbonyl, has to have been the carbonyl, not part of the carbonyl, but the carbonyl, right? So that means that this could have attacked it, this could have attacked it, or this could have attacked it, right? When you really think about it, that's really, you know, the key is figuring out what carbon was the carbonyl. Would you guys agree that that's kind of how you solve this puzzle, right? It's really a puzzle, okay? This carbon is the key. So if this attacked it, what was the ketone like, right? CH3, C, not alcohol, but C, double bond O. And then the benzene. Does that make sense? If you thought, okay, maybe the CH3 attacked it, right? Then the carbonyl would be, right? Carbonyl, benzene. Does that make sense? And then I could have said, okay, maybe the benzene attacked it. And now my ketone would be that chain. Does that make sense? So really, I think the key, and you know, that's why I just want to ask the ones that I checked, that was key for you, right? Figuring out what carbon is this one. It has to be the one that's still attached to the oxygen, right? The carbon of the alcohol. And then it has to have two carbons coming off of it at all times, which it does, right? Because there's three chains, so we know it's a ketone. Does that make sense? So that's, I don't know, this is overly complicated because I put it like with the parentheses and this and that, but it comes out to be the three that we just discussed, right? The phenyl attacking, right? And then you can see the CH3, CH2 attacking, and then the CH3 attacking the carbonyl. So that's the next slide there if you want to. B is the correct answer. Does that make sense? You don't have that slide, the answer? Okay, I'm sorry, yeah. It's overly complicated anyway, so don't worry about it. But I think in the past I did it kind of like a little like raise of hands, like which one do you think it is? But I think it sometimes just looking at it gives you a headache.
Yeah.
So I think the explanation is a little bit easier. Yeah. And then of course, right, Grignard is one kind of organometallic. We also have the organolithium, and it's really the same situation, right? But it's instead of having magnesium, I'm going to have lithium. So when this is forming, I think, yeah. So this is with the 3,3-dimethyl-2-butanone. But again, if I look at this, I have to figure out what's the nucleophile, and it is benzene. Does that make sense? It's whatever's attached to the lithium. So the benzene is going to attack, right? This is going to open, and that's what you see here, right? The salt, and then of course you just have to add your acid, right? And that forms your alcohol. Does that make sense? And then again, if I look at this product, is this the only way to make this product? No. This is one way. How many ways are there?
2, 3.
Right? This one that we just talked about, I could add this, and I could add the CH3, right? It's really the same question, just a different looking product. Does that make sense?
Another question. Wait, could you repeat that?
Mm-hmm.
It's
My question was the same as the previous question. If this is a product, right, I gave you one way of doing it. Is that the only way? The answer is no, right? Because you could have, right, this as a ketone, and then this is attacking it, right? I could have this as a ketone and the CH3 attacking it. So that's two other ways I could make this same exact product.
So all the alkanes, you're going to have three different.
If it's tertiary, you're going to have three ways. If it's secondary, you're going to have two ways. And if it's primary, you can only do it one way because you have to use formaldehyde. So you're kind of stuck. So, but it's because these have three carbon chains attached. So you get three ways. Yeah, if it's tertiary, three ways. Secondary, two ways, right? But the primary, it kind of locks you into using formaldehyde, so there's only one way to do it. Now, these give you higher yields. Why? What do we know about lithium?
It's really small.
Not just this, not really the size, but it is the difference in the dielectric, right, constant. So lithium is more electronegative than magnesium. So there's actually, right, more reactivity in this bond. But, you know, you can use either. Doesn't mean you should always use lithium, okay, but what did I take off to make it an ion like this?
It's H.
An H. Right. Does it mean I can only add 2 carbons? No. Right? I can actually make the chain over here as big as I want, as long as I have what? An H at the end, right? So there's actually more flexibility. I think I said you can add 2 just from that example, but you can actually, you know, add more carbons on one end, as long as there's still 1 hydrogen, right? So then sodium, right, amide is going to come in, right? That's a strong base. Strong bases like to take the protons, right? And it's going to leave you with the ion, right? And then that ion is the nucleophile, right? Again, if you're trying to figure out what's the nucleophile, what's going to do the adding here, right? It's going to be the carbon. So again, it's going to add to the carbon of the carbonyl, right? The pi bond opens, and you now have your new bond. And then, of course, you add the acid at the end to make the alcohol. Does that make sense?
So it's an alpha, see what they get.
If you were to add Na and H2 to the atom after that, would it take H's off both?
It would add the other H too. Like, if you did it here, it would have to take this H over here.
Okay.
And then what would you do?
You can add more
What's your
stuff.
play? What's your play there,
You
sir?
can add more stuff.
So yeah, then you could add more stuff. That's true.
It would only take about the triple bond, not the O.
Well, then it depends on pKa, right? The pKa of this is about 25. The pKa of this is 16. So which one is it going to pick off? The stronger acid. So if you're adding the Na and H2 here, then you're going to take off this hydrogen because it has a lower pKa, right? But here, there is no H yet. So if you want to add more stuff, you're going to have to add it before you create the alcohol. Does that make sense? Right? So you have to consider pKa as to what is going to happen. So if you add it to the product, then no, you would not end up being able to make, you know, that H would not come off of the alkyne. And then the next one here is just showing you some hydration steps. So what can you do once you have these, you know, the triple bond added, right, the alkyne ion added? Then you can go to chapter 7, and all of those reactions of triple bonds can be done on this side, which adds a variety of different products that you can do. And so this is just hydration being shown here, but you can do lots of other reactions as well. So you're also adding, right, this ability to react the triple bond. And you can even react the double bond by doing what? Taking the triple and making a double. What would I have to do? If I wanted this to be a double bond so I can do all of the reactions of chapter 6, what would I do? Reduction, right? Or hydrogens. Add hydrogens, right? Does that make sense?
Yeah. Makes sense.
Would reduction affect my alcohol? No. Would my reduction affect my carbonyl?
No.
Yes. And eventually we'll talk to that, you know, as to what it can do to the carbonyl. Do you know what I'm talking about when I say a reduction?
Would it break the?
Adding hydrogens, right? So imagine that I added hydrogens to the carbonyl, right? That's going to have an effect, right? I'm going to end up with an alcohol there too. So that could completely change, right? Game changer also. And we'll talk about that towards the end of this chapter. There's a lot in this chapter, so this is just the baby steps here. But does this make sense though? Figuring out what the nucleophile list is really key. And then of course HCN, right? The cyanide as the nucleophile, right? Again, this is going to be your nucleophile. The C is going to be the carbanion, right? So it gets added to the carbonyl, right? Pipe opens, add acid, you get an alcohol, right? And again, what can I do then with that cyanohydrin, which is what this is called when you have a cyanide next to an alcohol, right? So then you can do a bunch of different reactions. This is showing you the addition here. But then you can actually take them and make hydration reactions. You can make reduction reactions. So I mean, again, it opens up a variety of different things that you can do. So these are really useful starting materials for a number of different syntheses. This is where we'll stop for today. So again, the homework should have opened today at 10 o'clock, so if it didn't, let me know. And we're going to go all the way through Monday with materials, so should be plenty of time for the homework, but don't, let it get behind. See if you can get started on there as soon as possible. And let me know if you have any questions. Please bring your OWL notebooks by. I'll just check them so you can have them to use, but please come by so I can give you those points. I'm not going to accept it after Wednesday, though, okay? So come by between now and Wednesday if you haven't turned it in already. Thank you very much. Oh, there's a careers in science today. I was supposed to tell you. So 12:15 in Founders 104. It's an engineering student who was a student here and has gone to Columbia, so she'll talk about that.
Maybe I'll order it. Huh? Yeah.
Order it.
Oh, then I would have to do it again?
Yeah.
Negative. All right, but again, just backtracking a little bit here. So we've already covered this material, but I just wanted to go back and reiterate the pattern, right, that we're trying to achieve, right? So these are nucleophilic additions. So what do we have to identify? No leaving group really here, but we have to identify the nucleophile. It's a nucleophilic addition. Yeah? So when we look at these are the ones we've done so far last class. We're going to add some more today. So what is the nucleophile of a green yard? The R, right? Whatever that R is, it can be 1 carbon, it can be 10 carbons, it can be a benzene, any carbon, right? That's what R means, but it's the R, right? What's the nucleophile in an organolithium? The R, again, right? 1 carbon, 10 carbons, a benzene, a cyclic, you name it. Does that make sense? Like you just have to identify that. What's the nucleophile in this alkyne ion?
The carbanion.
The carbon, right? The carbanion with the lone pair, right? Not the R this time, right? Because the R is telling you this can be a big chain, but it's going to be attached right here. That's what's attaching to the carbonyl carbon. What about in this one?
Carbanion.
The carbon also, even though nitrogen does have a lone pair, right, naturally, but it's not charged, right? So you're going to go to the carbon because it is a negative charge. Does that make sense? Like again, it's really about identifying this pattern. This is a nucleophilic addition. And then I'm adding this to the carbonyl, right? And how do I add, but not with a leaving group, but by doing what? It's a double bond O, right? So what am I going to do? I'm going to break the pi, that extra bond, right? So that instead of it being double bond, my carbon is now going to have all single bonds, right? That's that tetrahedral product that I end up with. Does that make sense? So that is the pattern. In every reaction that we're going to do, it's going to follow, right? As long as it's a nucleophilic addition. If we switch, I'll let you know. Okay? But so far, that's what we're doing. Does that make sense? So over and over and over again. Okay? So when we go to a new reaction, what are you going to identify first? The nucleophile. Thank you. Alright, so we did all this. Did all this.
I think we were on it.
Right here.
Are we?
Yeah. So we did the cyanohydrins. These slides are just showing you what happens once you do the addition. For instance, when you add the cyanyl group, what can you do once you do that? Then you can transform the nitrogen, right? So you can do dehydration. That's the first thing. You can also do catalytic reduction to get the amine. So that's what this is telling you. Some additional reactions you can do. But this is really the new one here. Okay, so now what are we going to do? We're going to produce alkenes. How?
Using the Wittig reaction.
Wittig reaction. Okay, you're being very literal. I want you to follow my pattern. Does my pattern work for this reaction? Do you see a nucleophile?
Yes.
Right? These are still, these are carbenes. Remember those? They're not carbanions because it's a carbon with 2 hydrogens and a negative charge. So it's a carbon without all the valence electrons. So this is a type of carbon we've already talked about. But they are nucleophiles, right? Look at the negative charge. Does that make sense? So guess what the alkene is going to have? A nucleophile. Right? Does that make sense? So this was not here, was it? It was an oxygen. And what am I adding to that? The carbon. Right? Now it is a little bit different because instead of getting a single bond, right, there is no alcohol in my product. It's an alkene. So what you really have to consider is, how do I do that part? That's new, right?
That part.
But you still should realize I'm adding whatever the nucleophile is, right? The CH2 is what I'm adding. Would you agree? Now the question is, well, but how do I end up with a double bond and not a single bond, right? That's really the question here, and this is how. So these are done, by the way, with what we call elides, and they're phosphonium elides. So the phosphonium, right, phosphorus there as an ion. And the way that you form these elides is by reacting triphenylphosphine. Okay, so you usually abbreviate PH3, right, 3 phenols, 3 benzene rings. Okay, and then the phosphorus, okay, that picks up a carbon from what? An alkyl halide, right, which we've been seeing over and over again. The halide is your leaving group, so this is an SN2 reaction, right? Okay. And then it's going to give you the product. And of course, the product is a salt, right? So you see that the phosphorus is going to be positively charged. But right now I have a CH3, and that's not really going to help me. That's not a nucleophile in this situation. So what has to happen is you treat that phosphonium salt, right? It's an ion at this point here, okay, with a very strong base. And you can do butyl lithium, okay, sodium hydride, or sodium amide, which we've used before in other reactions. And so when you do this, it's going to, the strong base is going to take a hydrogen away, right? That's what bases do. They accept the proton, okay? And so now the electrons go back onto the carbon, and now you have your nucleophile. Does that make sense? So it might ask you, Al likes to ask this question, how did you form the elide? Okay, so they're going to give you the product, and if the product is a CH3, how did you form the elide? From a CH3, right? Does that make sense? So this is how you do that, the reaction there. So once you have the elide, then you attack the carbonyl, right? So the carbon of the carbonyl, so that's what's shown here. So again, your nucleophile initiates it all. That's why it's so important for you to start out by asking what is the nucleophile, by identifying that in your reaction, because that's going to be the starting point. So it attacks the carbon, right, of the carbonyl. The pi opens. So again, we've been seeing this over and over and over again, right? It gives you, right, that tetrahedral carbon. Okay, there's 2 R's, so you know it's going to be tetrahedral there. But what's different about this is that you end up with a negative O in really close proximity to a positive ion, which is the phosphorus. And what ends up happening is when positives and negatives are close together, right, you can form a bond. Does that make sense? So that's really what's different about this, is that it puts the oxygen really close to the phosphorus, and then a bond forms. So the intermediate here is a oxaphosphatane, excuse me. That's the product, which is really, right, a 4-membered ring. Okay, does that make sense? What's different about this mechanism? Does everybody see that, right? All right, so then what's going to happen, right? So then in the second step, that intermediate, it's going to fall apart, okay? Or they call it decomposition of the intermediate, because what really, this isn't, right, a very stable molecule. Okay, so again, remember cyclic compounds, right? 3 carbons, 4 carbons, right? 5 carbons. Their angles are not very close to the ideal 109.5, right? So there's a motivation to break that cycle. So that's what's going to happen here. So when it does, though, notice what happens. The O bond, okay, is going to break, forming a double bond here, right? So it should be P double bond O, right? And then the P carbon bond, right, phosphorus carbon bond also breaks, which makes it a double bond between 2 carbons. And that's how you get an alkene. Does that make sense? But the nucleophile attacking the carbonyl part is exactly the same. The difference is this right here, that the O, negative, right, negatively charged, which we see it with every reaction so far, okay, in this chapter, is really close to that positive phosphorus. And then the bond forms, but only temporarily. It doesn't want to stay, right, in a 90-degree angle situation. It wants the angle to go back to 109.5 if it can, right? And so it finds a way, right, of breaking it here. Is the angle 109, by the way, here?
No.
No, it's 120, right? Okay, but these are stable molecules, right? Planar molecules are much more stable than a 4-member ring. Does that make sense? How we end up? But again, right, if you're thinking about what's getting added, it's still the nucleophile. Would you agree? The pattern is still there. The difference is what happens once you have that addition, right? Then the proximity of these two, the oxygen and the phosphorus, causes the intermediate to form. Does that make sense? And then the intermediate decomposes and you get the double bond, right? That makes sense? So this is a nucleophilic addition still, it's just followed by that decomposition of the oxyphosphatane intermediate. All right, so let's see some examples here. So we have acetone, which you agree has a carbonyl, right? Acetone has a carbonyl, right? And then you have an elide, right? How do I know it's an elide? What's my clue? The phosphorus, right? So that's going to look different from all other reactions, right? That's going to kind of be your signature. Okay, I know this is going to follow that particular mechanism. I'm going to go to my reaction sheet, and guess what? It's going to be there. And it's going to show you that you get the alkene, and that the nucleophile is the R group, right? That carbon chain. So what's the carbon in this one? What's the R, the nucleophile, in this first reaction? 1, 2, 3, 4, 5 carbons. Not 1 carbon, right? Not just the CH2, the carbene, but, right, 5 carbon chain. Does that make sense? So what are you going to expect then, right? That this carbon attacks the carbonyl opens, right? And then, like I said, because the phosphorus and the oxygen are going to be close together, they're going to form that intermediate, which is going to collapse to give me a double bond, right, between my carbonyl and my carbon, right, that got attacked, or sorry, the carbon of the nucleophile that attacked the carbonyl. Does that make sense? So that's really what you get there, the double bond, right? But it's still 1, 2, 3, 4, 5, right, from the nucleophile, and 1, 2, 3 from the carbonyl, right? That hasn't changed. Does that make sense? So what about the next one? So phenyl acetaldehyde, right? Again, do you agree there's a carbonyl, right? Okay. And then you see, okay, it's an elide, right? How do I know? There's a phosphorus, right? And then you're going to decide, what is the nucleophile? Right? 2 carbons now, right? It can be different lengths, but it's a carbon. So again, that's what's going to attack, open, right? Intermediate see it collapses and it forms a double bond between the carbon of your nucleophile, right? So that's what you've added, 1, 2. That makes sense? So what about down here? Right? When you identify it's a carbonyl, the elide, right? Nucleophile. That makes sense? So again, you're going to have, right, the bond is going to be this one as a double bond, right? Can everybody see the pattern here? I'm going to do the same thing for all of these reactions. Now, do you notice anything different in the product?
Well, if it's on the primary,
Right. So these, why aren't these E or Z? This one up at the top.
because that's on the secondary.
No. Because these two carbons are the same. So I cannot tell if it's E or Z. So that one doesn't get one, it just gets one product. But would you agree that when I look at this, there's an H I don't see, right? Or, yeah. There's an H I don't see over here, right? So I can do E or Z, and I actually get both, but I get much more of the Z. Does that make sense? 87%. And we're going to get into the why of this, but do you notice that you get a split, right? But the split is much more favoring here the Z product, right? Then if we look at the third reaction, I get only the E, get no Z at all, right? Again, you look at this and you know there's H's coming off that you don't see, right? So you know you can do E or Z, right? But you get only E. So what's the difference? Okay? So the difference is, okay, on what's attached as part of your nucleophile, your elide here. So this is just a carbon right here, right? Okay, there's nothing really to pull those electrons away or, you know, make this any more, right, nucleophilic than it is, right? There's nothing here that can change, right, that negative positive interaction, right? So when that's the case, when you don't have any what we call electron withdrawing groups, that's really the key word there, but you have nothing to pull electrons away, right, electron withdrawing, then you get mostly Z. You get a little bit of E, but mostly Z. So would you agree that in your elide down here, you do have something to pull electrons away? Would you agree? There's a conjugated system with a very, or actually both here, right? Two very electronegative atoms. Guess what the charge is going to, where the charge is going to go? Away from, right? So when you have this, your product is just one of the isomers and it happens to be E all the time. So if the nucleophile basically is more concentrated, it gives you Z. If it is less concentrated, right, that charge is less concentrated on the carbon, it's going to give you E. Okay, and so that's something you want to consider for this reaction. And the new bond is the double bond, as we said there. Okay, and so this is what I just said, but in a slide for you to have it as a reference. So if you have, again, that anion, right, that stabilizing, pooling electrons, right, if you have that, that's what you're trying to consider. Do I have it or don't I have it? Okay, if I do have it, like the resonance structure here, right, the conjugated system, it's going to be E selective. Okay, if you do not have that, like just a carbon doesn't have anywhere for the charge to go, there's no stability there, okay, it's going to be Z. So this is something to consider about these Wittig reactions. So pay attention to what's right next, neighboring that carbon of the carbanion. Okay. So this is the Wittig reaction. So again, what is the anion stabilizing group in this page?
The P.
Not the P.
The anion stabilizing?
Yeah. just talked about it. If you have an anion stabilizing group, it's showing you what an anion stabilizing group looks like, right? A system that's conjugated. Do you see a system that's conjugated on this page? The bottom one. Right? That makes sense. What you're looking for. Right? That double bond O, that's your stabilizing group.
Okay, so if it was just an O, it wouldn't make a difference.
It's the conjugated system with the electron group. So it's usually either a ketone, an aldehyde, an ester, a carboxylic acid. All those groups have carbonyls. So the groups we're going to be talking about, right, this chapter, next chapter, 18 and 19. All of those are anion stabilizing groups. So this is an ester, by the way, the one on this example. But it can be an aldehyde, a ketone, carboxylic acid, ester, okay, the ions of those, acid chlorides, acetals, lots of different groups, but it's really that double bond O group. Okay? So that's the Wittig reaction, right? So when you're doing this example, right, think about these things that I'm talking about, okay? I mean, the grades on OWL are great. So I know that you're spending due time, but you really want to make that time work for you when you go to the exam, right? So think about what I'm telling you to think about, because that's what I'm going to try to see if you know in the exam, right? So I know there's ways of getting 100 on OWL without really understanding the question. I know that. And you know, I mean, hey, it is what it is, but you should use that time. If you're going to spend 3 hours on OWL, you might as well make those 3 hours worth more than just, right? So, it's just me, my 2 cents.
Seems like a lot of extra work.
Okay. All right, so now we talked about the Wittig reaction, we talked about our organometallics and the 2 carbon ions. So now what about if I want to add water? What's my nucleophile for water? OH, hydroxide ion, right? Okay. So does it follow the pattern here? What's the water going to do?
Come in.
Going to
Attack
attack,
the carbon, break the
open,
double bond.
right? But I'm going to have a situation where I have, right, a hydrogen, too many here, and a hydrogen, too less here. So we're going to see again, how do we get this actual product? But does everybody understand that it's still a nucleophilic addition? I'm adding a hydroxide ion, right? Which, because of the way it is, there's an oxygen already at the carbonyl, which becomes an alcohol, right? And you're attacking with something that also becomes an alcohol. The product is what we call a gem diol, or a geminal diol, excuse me. So geminal, you know, Gemini. Anybody a Gemini here? Any Geminis in the house? No? Okay. I'm May 19th, so I'm 1 day off of being a Gemini, so I'm Taurus, proud of it. Anyhow, that's where the word comes from, right? Gemini, the twins, so having 2 of something attached to the same carbon. So it's not really just a diol, right? Because a diol is a neighboring carbon. Here, they're both off of the same carbon, so they are twins, right? Off of the same carbon. So this is the product of a addition, right, of water in this situation. This is also called a hydrate. We sometimes see these as intermediates with aldehyde reactions. So, and then we call them a hydrate. So here's formaldehyde. If you put formaldehyde in water, and we kind of talked about this, formaldehyde is a gas, and you can put it into solution, into an aqueous solution, 37%. That's going to be formalin, which is embalming fluid. So what's happening to the formaldehyde when it goes into the water? Well, again, the water is going to attack, right? The carbonyl is going to open. Okay, and then what you're going to get is 2 alcohols. So you get the formaldehyde hydrate, which is, again, a gem diol. Okay? Same carbon, off of the same carbon there. Okay? And so because we have a lot of moisture in the air, if you have small aldehydes, they tend to form the hydrate, whether you want them to or not. So we have to keep our aldehydes. Butanol is okay, but the 3 carbons, 2 carbons, and then formaldehyde, they tend to react even with the moisture in the air. And when they're hydrates, they really don't react like aldehydes anymore. So if we try to do a reaction at this point, expecting, right, that you have a carbonyl, you actually don't have a carbonyl anymore. It's 99% hydrate. So it doesn't act like you would expect it to anymore. Okay? But what about acetone, right? Acetone is not an aldehyde, it's a ketone, right? It's the smallest ketone with 3 carbons. So when you put it in water, right, yeah, potentially you could get the hydrate, but it is not a very, doesn't happen very often. So is acetone something we can leave out? Yeah. It can't leave out because it evaporates, you're right. Not with the bottle open, but I mean, we have a bottle of acetone there for however long we want, right? Until we use it up. But I mean, it's not unstable. I said that incorrectly. You're right. If I leave it open because it's so volatile, you know what she was saying, right? Like nail polish remover, if you don't close it all the way and then you go to use it and it's gone, yeah. I understand what I meant more so in the hydrate state. There's not going to be any acetone. It's always acetone until it's gone. Yeah, I asked that question. It wasn't a good way to ask that, but very little of the acetone gets, you know, reacts with water, so it does not transform. But aldehydes are very sensitive to that, so that's the difference between the two. Okay. So what happens really then if you're adding an alcohol? Okay, so this is where it gets interesting. So now you have to pay attention to how many moles of the alcohol you have as well. Okay, so let's talk about that. So the addition here, though, what's the nucleophile in an alcohol? Right, the OET here, meaning the alkoxide, right? So it's an alkyl chain. This is 2 carbons, but with an oxygen, so we call that an alkoxide. Does that make sense? So it's the alkoxide. And when you do that, again, when the nucleophile adds, you're adding the alkoxide, and then the carbonyl becomes?
The 2.
This is the nucleophile. It attacks, opens, so what do you get? Alcohol. Thank you. Alcohol, right? Does that make sense? And again, we've been seeing this over and over and over again, right? So if I drew all the products we've talked about so far, what would they all have in common? If I drew them all here, all the ones we've talked so far, what would it be in common? The alcohol. They all form the alcohol. So that, again, is a pattern. Follow the pattern, right? Does that make sense? What's changing now is, what's the nucleophile? What am I attacking so that you form the alcohol, right? That has changed. So what is a molecule, or what do we call a molecule, that has 1 alcohol in 1 alkoxide ion, right? Together, or an alkoxy group. That's called a hemaceto. Okay, so hemaceto is a molecule with an OH and an OR, which is called an alkoxy. So it came from the alkoxide ion from an alcohol, off of, again, the same carbon. So not neighboring carbons, but off of the same carbon. So that's called a right? Acetal. So what happens if I have 2 moles of alcohols? What can potentially happen? Not a diol, but this is hemi, right? Half. So if I do the reaction again, I'm going to have a full acetal. And that's the molecule. So with 2 moles, what's going to happen with 2 molecules of the alcohol, right? This is a leaving group. Would you agree? We've talked about how this can be turned into an oxonium ion, and then the oxonium ion leaves. So if you have a nucleophile and, right, an OH group, I can always make that leave, right? And now you would have 2 alkoxy. Does that make sense? And that's called an acetal. I don't know if I have that here. I just have the hemacetals at the back. Oh, there's the acetyl, but I have a lot to talk about before we get there. But that's basically what that little clue up at the top says. What happens if you had two, right? Two alcohols? Then you would get an additional attack. Does that make sense?
Instead of the OH, you would have the OUT.
Yeah, so basically once you have this, you're gonna go again, right? So once you made your product, right, then if you had more alcohol, it would react again, right? So this would attack and that would leave. That's what I'm saying. Right? Of course, you would have to add an acid, and I mean, you know, there's a mechanism, but do you understand again the pattern? The pattern is the nucleophile attacks, right? But in this case, the leaving group is going to leave. If you have 2 moles, only if you have 2 or more moles.
The OH would leave.
Right? The OH would leave, because we know, we've seen reactions of alcohol, so we know we can make that into a good leaving group, and then the OH leaves,
Then it
right?
won't
We've
have
done that.
two.
And then what that gives you as a product is now, right, the first one is still there, and now I've added another one. Right, and then like I said, this is called an acetal, right? 2 alkoxys, where this is half, right, half an acetal, because there's still an alcohol there. So we call it hem, right, hemi.
So this is the only one with 2 moles that will form an alcohol.
Yeah, so with 2 moles, you would not get the alcohol anymore.
You get two.
Okay, but that's, again, a clue for you, right? You want to look for this, like OWL will tell you 1 mole or 2 moles, right? Or excess, right? Excess means 2 or more moles, so you want to clue into that depending on what you want, right? The hemiacetal or the acetal, you'll have to make a choice as to how much of the alcohol to add. Does that make sense? So.
It makes sense.
So-
Thank you, Doctor.
All right, now hemacetals are really important in biochemistry, in biological systems, and the reason is because they actually participate in the cyclization reaction. So when you have carbohydrates with 5 or 6 carbons, okay, they actually will rather be a cyclic structure than a linear structure. So we do look at glucose, right, as a linear structure, but in biological systems, 99.9% of glucose occurs as a cyclic structure. Okay, and this happens with this reaction we just talked about. So these are different examples here at the top. But this is glucose, right? And notice that it's a carbonyl, right? And then there's a bunch of hydroxyls that I can choose from. Okay, but the stability is usually in forming 5 or 6 membered rings, right? 3 membered rings, way too unstable, right? 4 membered rings, still way too unstable. 5, it begins to be possible. 6, even better. Does that make sense? So if I use this one, would it work? My ring actually would only have 2 carbons, which we don't even have a ring for, right? This carbon would form 3 carbons, right? That's too small. This carbon would form 4 carbons, too small, right? So really, the first one that I could react is carbon 5. Does that make sense? So carbon 5, the hydroxyl group, is going to attack the carbonyl. The carbonyl opens. Okay, and what you form is this bond in red here. Okay, so the oxygen is attacking, right? So the bond is between O and the carbon, right? O and the carbon. And then remember, the carbonyl always becomes a alcohol, right? Just talked about that. See it? Okay. So in the one above, again, right, you want to consider that you need to have 5 members in your ring. 1, 2, 3, 4, 5, right? Does that make sense? So with this one, right, too small, right? Too small. 5 is the one that forms the more stable ring, which is the 6-membered ring. So again, in biological systems, that's what you see. I don't know who had their hands up.
Why are there 2 different versions of
Because again, remember something, a theme of these reactions is that you always form in racemic, because the carbonyl is flat, it's planar, so you can attack from one side or from the other side. So you really should always draw two. 50-50, racemic mixtures. That's another theme if you go back to the beginning of this chapter. That's why.
So we need to count the carbons where an OH is attached to know where.
Yeah, because the reaction here is between an OH and the carbonyl.
Okay.
So you're actually counting members of the ring, which this is a heterocycle, right? So there's carbon and a hydrogen as part of the cycle. Does that make sense? So you're actually counting carbons, 1, 2, 3, 4, 5, 6, right? The oxygen counts 2 because it makes up the cycle.
Yeah.
Does that make sense?
And it attaches and closes the ring.
But this is a very important, again, reaction in biological systems. This is how carbohydrates exist. And so this is acid catalyzed, usually, these reactions, but they can be base catalyzed as well. And it actually, when you think about it, right, what you really need in order for a nucleophilic addition to happen faster is a better nucleophile. Would you agree? That's really the only thing that you can really change. The carbonyl is the carbonyl, right? And you can attach the OH, that's the hydrogen part, the acid catalyzed. But in a base catalyzed, that's something you can do to the nucleophile, right? So what's the base going to want? The hydrogen, right? That's what bases want. They accept a proton, right? And so when that happens, then you get your charged ion, which we call this one the alkoxide ion. So would you agree with me that the alkoxide ion is a better nucleophile than the alcohol? Yeah, it's charged, right? That makes sense to everybody? How a base would work? We already know how an acid would work by affecting the carbonyl oxygen. We saw that already. So I'm showing you that these reactions can also be done when there's a base present. So it's either acid or base catalyzed. So if you go back, acid base, see that? Acid base. We already know what the acid does, right? You see above the arrow. I don't know if you even noticed that, right? We already know how an acid works. We've been seeing that over and over again, but we've never seen a base catalyst, have we? Not so far. Right? Does that make sense? So what I'm telling you, these reactions can actually be done in either acid or base, right? So the acid, we already know how it works. But the base, here's what it does. It forms a stronger nucleophile. So that's the key here, is to get a better nucleophile. That's going to help increase the rate of your reaction. Okay, so then the nucleophile does what we've been saying, attacks the carbon of the carbonyl, opens the double bond, forms your tetrahedral carbon, right? And then of course we have to finish by adding a hydrogen, right, to the oxide ion. So you see that the alcohol can serve as that the source of the hydrogen in this last step. Does that make sense?
That's starting alcohol.
The alcohol at the end is OR. The OHR, that's the alcohol. Does that make sense or no? I don't feel like this makes sense. Does this
That
make
makes
sense?
sense. But we got that alcohol from the starting from step 1, that's what I'm saying. To come back in step 3 to donate that hydrogen to give
Correct.
us.
Well, but remember too that this reaction is being done with a lot of alcohol, right? The alcohol is going to be usually in excess, unless you're trying to regulate how much based on whether you want the acetal or the hemaceto, right? So, but the assumption is there are additional alcohol molecules, right? 1 mole of alcohol is not one single alcohol, right? It's how many?
1 molar mass.
1 mole is what? A mole is what? A mole is what? Please don't. Thank you. Right? Everybody's number. I was like, I can't. 6.0 O2
10 to the 23rd.
times 10 to the 23rd. Is that 10 to the 23rd? Is that one thing? That is a lot of things in that 1 mole. Does that make sense? So we're not talking 1 alcohol in there, right? We're talking 1 mole of alcohol. I was going to say, did Dr. Johnson not teach you about a mole? I forgot this number. Just kidding.
We learned that.
We learned it, right? We have Mole Day, right? We celebrate Mole Day. When is Mole Day?
Probably in June.
When is Mole Day?
I want to say something.
It's October 23rd. 10 to the 23rd. At 6:02. All
I'm really
So-
happy we record these lectures.
Well, now you have access to it. What I ask is that I not end up on YouTube, please.
Too late.
All right, too late. Too late. There's gonna be a montage of me just going like that. You know,
And
that
you'll
sound,
be
that sound
And you'll be
alone.
rich.
There'll be a
You'll have
Burke
so many
meme.
views. You'll get
There'll
paid.
be a Burke
A
meme.
Burke me, I don't even know what a meme is.
Does that make sense? Does that make sense?
Okay, but again, I just want to reiterate that with the base, what we are trying to do is to make that nucleophile, right, a better nucleophile by making it an ion. Okay, so that's really the key to this. Again, with the acid catalyzed, we've already covered this, so but I put it right here to review. Again, if you have an acid, then the proton, right, it's going to protonate the oxygen of the carbonyl. Okay? And so then there's even more of a drive for the pi bond to open because the oxygen doesn't really want to have that positive charge. And so the nucleophile then doesn't have to be quite as good, right? Because what's the driving force? This charge right here that I just created. Does that make sense? Okay. And then now, what's my problem? I already have my alcohol over here. So what do I have to do? Not add a hydrogen, but remove one, right? In the base catalyzed, I needed to add, if I go back, right, at the end, I have an ion, and I need to add a hydrogen, right, with the base. But with the acid, I've already picked up the hydrogen all the way up in the first step for my alcohol, right? But what do I have to get rid of here? The hydrogen, right? So it's a deprotonation step at the end. Does that make sense? So what does a base do? By deprotonating, not adding a hydrogen. What does a base do? A base, not an acid. A base takes away a hydrogen. That's called deprotonation, right? Removing a hydrogen, deprotonation. Yeah? So it's deprotonation, it's not, right, in this slide though. This slide, right? The base deprotonates, makes my nucleophile, right? And then I need to do what at the end? Protonate, right? So it's deprotonate, attack, protonate. What's the acid like? Just the opposite, right? Protonate first, attack, deprotonate. Does that make sense? They are really inverse reactions.
So bases deprotonate, then you have to protonate them, and then acids you protonate them, then you have to deprotonate them.
Correct. Because you started by adding the hydrogen. At the end, you're going to have one too many. You've got to get rid of that. In the base, you're removing a hydrogen, so there's going to be a hydrogen missing, so you have to add that at the end. Does that make sense, what the process is? So you can either do it with an acid, or you can do it with a base. But they're really inverse processes, right? Giving you the same product, though. They don't give you different products. They give you the same exact product. They just do it in different ways. Does that make sense? Do you think one is better than the other? Which one would you go with if it was you? If you had to choose, you were the organic chemist, lead organic chemist, and you're telling your minions of scientists to do the right thing, what would you tell them to do? Use an acid or use a base?
It depends on what you want.
Base.
You get exactly the same product. You get exactly the same product.
Does it matter?
I was still told
Depending on what
base, though.
chemicals you'd have to
Yeah.
use.
I would say base.
Base.
Base requires less steps later, you'll see. It will all make sense. But a base is actually, in these kinds of mechanisms, used more often than an acid. With alcohols, acids are always better. But with carbonyls, bases tend to work better. And we'll see it more of it, and you'll appreciate it because there'll be one less step later. Right now, it's 3 steps each, right? Protonate, attack, deprotonate, or you do the opposite, right? Deprotonate, attack, protonate. Same thing, 3 steps. But later, bases are going to actually remove a step. So, and it's all measured by yields, and bases tend to give you higher yields. So ultimately, as an organic chemist, that's what you're measured by. Like, what was the yield of that reaction, right? The higher the yield, the better the reaction. All right, so this is an acetal already talked about. So if you have, right, 2 moles or more of alcohol, then you can, go all the way, as you might say, all the way to what? 2 alkoxy. So that's an acetal rather than a hemacetal. So, and then this is just showing you this is acid catalyzed, right? See the protonation at the top, right? You're adding the proton, right? Making that oxonium, which is going to be my leaving group, right? And then you form carbocation, and then the alcohol can come in as the nucleophile and attack the carbonyl, right? And so then you, again, need that last step to remove the hydrogen. And then you get the acetal, right? 2 alkoxy groups. Right? The alcohol was removed as water in step 2. Can I do the same reaction with the base?
No.
No. Why not? The same one I just did, why not? What's the issue? This first step.
It doesn't have a double bond on
Because it
the
doesn't have a double bond, so the most important thing is, this is a reaction of alcohol again, right? The important thing is to create the leaving group. So the hemacetal reaction, that first, right, transformation can be done with either acid or base, it doesn't matter, right? But the second step is going to require an acid. Does everybody understand the difference here? There is no double bond anymore, right? So you have to add the acid in order to get the oxonium ion, which is water, right, as a leaving group. So that step 2 can happen. If I had a base, that wouldn't happen, right? Does that make sense?
And then you need step 2 to happen to have the
In
double
order to
bond.
be able to, reform that double bond and then attack with the alcohol, right? Do that. This would not be possible. Step 3 would not be possible without step 2. And step 2 requires the acid. So that's,
So you can't do double bond, you can't do a base because there's no double bond.
yeah,
so
because
that-
it's back to an alcohol
acid.
again. And alcohols work,
and acids
yes.
are together.
That's how that goes. We don't see those reactions with base catalysts. So,
For addition of
yeah, nucleophilic additions, because they're 2 double bonds, they can be an acid or base, but nucleophilic substitutions are an acid. All right, so what if the nucleophile was nitrogen? Right, so we've seen now a variety of different things that we can add, including carbons, right, including water, including alcohols. Now, what about nitrogen? So nitrogens are great nucleophiles. Would you agree they already have a lone pair, right, as part of their neutral molecule, so they tend to be great nucleophiles. So again, if you're looking at this reaction, you're going to take, right, which one is my nucleophile? And I know the lone pair is in there, and I know there is no charge, but again, right, you want to consider that nitrogens are great nucleophiles. So the nitrogen is my nucleophile, not my carbon, right? The nitrogen. That makes sense. And then what's the nucleophile going to attack?
the carbon.
The carbonyl, right? The carbon of the carbonyl, this opens up, right? Okay? But again, when I look at the product, that's kind of funny looking, isn't it? I'm back to that double bond business, just like the Elides, right? Does that make sense? So again, there's going to be something that happens in the intermediate that's going to lead to that. But again, what is the new bond between the nitrogen and the carbon of the carbonyl? Would you agree?
Double bond.
Right? But it happens to be a double bond. So we'll look at the mechanism to figure out why that is next time. These are called Schiff bases or Enamines. So it would be great if you broke out the book and did some reading on Schiff bases. I think that would be a wonderful idea. So, 2 cents. Yeah. This is where we're going to stop. So go ahead.
So how would you tell the difference between what the nucleophile here, because there was a nitrogen in one of the previous examples, but we didn't use that as a nucleophile. Like it's like slide 25. Or was one of the
Yeah, this one is totally different situation because I told you that the carbon, right, if I go back a little bit more here, the ion of a cyanide is actually the carbon. See how the carbon is carrying the negative charge, not the
Okay,
nitrogen.
so there's a negative charge.
This carbon does not have enough bonds. It only has 3.
Right, okay.
The carbons that we're talking about now that are attached to the nitrogen as an amine, they are carbons that have 4 bonds. They're happy carbons, not ions. Happy carbons. Yes, good question though. Yeah.
This is just a question, so do we have school on Monday? Of course. We do?
Yes, that's President's Day, but we do not, we don't always on President's Day.
Not for this president.
So I just wanted to make sure.
Well, it doesn't matter who the president is, we never quiz. Whether you like the president or not, you can celebrate him without school closing. Yep, so that's where we'll stop. So again, remember Monday we'll do problem 8 from the exam as a challenge. That is a challenge, so spend some time and work on it. Okay, try to think about it. Of course, come by, email me if you have questions. Talk to your friends, I guess. They might have gotten it right on the exam. I don't know. Thank you very much.
We did it.
So you do have to, do it in a certain order so that you don't end up with 2 salts, right? So if you were doing a William ether synthesis, for instance, so that would be, where the order of those steps would matter. So not that there weren't other ways to accomplish that problem. So you might have found an alternative that's all right too, and I'll consider that first. Okay. But I think something that, I was talking to Dr. Johnson, and, sometimes you just kind of, just trying to think of a way, like, I just think that's what's missing from, your ability to do significantly better on the exam is being able to figure out these mechanisms, right? I think that's really what's pulling the grades down. And so, I thought of something really, like, what to me is very straightforward. So if I drew this, and I said that I wanted this as a product, right? In those many steps, right? Like this to me is very straightforward. Is it straightforward to you?
Yes.
I think there's 3 steps. Is this straightforward to you? Or not?
Yeah.
How many people think like they could do this? Do it on your paper right now. me, I don't even think you should be looking at your reaction. Like, I think this should be so easy at this point that you shouldn't even need to look at your reaction sheet. I mean, all of the steps that are up on the board, we've done it so many times. So if you're looking through your reaction sheets, I'm worried still about your progress this far. Does that make sense? I mean, should be really easy. No reaction sheet required. I mean, I'm not saying you shouldn't look at your reactions, but if you are, to me, like, that's not, you know, you're not quite there. That's not the right place, right? To get it here, that shouldn't be there. Not water though, just some source of heat, right? Because this would be a different reaction, but that's, I see where you're going. Oh, you did it. You need BR2 first, right? Then you need to, it's 3 steps, not 2. Does that make sense, what you're missing? You need to turn it into the BR, then no heat though, right? Otherwise it would eliminate. The heat would eliminate, which, I mean, then you could do another step to make it the alcohol, but you don't need it, right? I mean, you can do it, like, that would be more steps, but this wouldn't be the next step after that. The ozone.
That's not good, sorry.
Okay.
Yeah, really weird.
So does this make sense? Like, what I'm trying to say at this point, like, this should really, I mean, this is the basic of mechanisms, right? And if I did something really easy like this, change, right? Start with the same starting material, but now I say that.
Yes.
Yeah, right? The beginning is really the issue here, because if you do BR2, right, with some source of energy here, it's going to put it in the most substituted place, right, which is where this one is leading you. But how could I go this way? I want it to be at the end, right? Right, so you want NBS or maybe peroxides, that will work too, right? Something that is radical. Does that make sense? Like, it's a very simple change. Does that make sense? Like, what I'm trying to say to you is that at this point, things like this should be boom, boom, boom. Like, you shouldn't even need to look at your reaction sheet. Like, this is really simple. Right? And so that's really, like, if you're not at that point, then we need to talk, we need to practice, we need to do something different, or this is going to be an issue. But most of you got this, all right, so I feel better about that. But if you're not getting this, and like I said, I think this is so simple and straightforward, you don't require a reaction sheet. Now, you know, not all mechanisms are like that, especially on the exam. But have you noticed that in a question that's A, B, and C, A is pretty straightforward, isn't it?
Yeah.
Right? And then B is a little bit more complex, and C is usually the harder one of the 3. Right? So, I mean, I do give you something this easy most of the time as a first, like, let's warm up, right? Then we do something a little bit, right, needs a little bit more. And then finally, the third sometimes is more of a challenge, right? So you should still be able to get, I hope, A and B pretty, you know, again, easy, right? And then maybe you miss some points on C. That's much better than what I'm seeing right now. Like, I'm seeing, you know, very low scores on these. So I just want you to think about that this is really straightforward. It is really straightforward. Does that make sense? So again, when you're working on OWL, I mean, you have a lot of opportunity to practice this, but you have to practice correctly. Use OWL correctly, right? And you know, once the homework closes too, or you turn it in, you can go back and work on those as much as you want without it affecting your grade. So, you know, once you've got 100, but there might be some that you're not so comfortable with, it's open for you to go back and look at those some more. Or come and see me and say, could we work on this one a couple of times together, you know, or something like that. Because I'm just worried that if we continue going the same way, that we're not really going to improve the grades well enough for you to get into an A or a B in the class, you know. And I know that's what you're aiming for, right? Getting an A or a B in this course, and you know, I would like you to do that as well. So just think about this. If this was really difficult for you, then you know, we might need to do some work together, and I'll be happy to do so. Okay?
What does no peroxide do?
Huh?
No
So the no peroxide is just going to put it in the most substituted. If you say peroxide, then it's going to usually be a radical mechanism, which could give you the least substituted. So that's the reason. And NBS is also a radical starter. So usually we think if we want it to be in the least substituted, NBS would work as well. All right. So but keep working at it, and of course we have lots of reactions in this chapter. Again, right, they're really the same reaction over and over again, but you have to figure out what is the nucleophile. So here we go now with nitrogen as a nucleophile. Okay, so far haven't seen much from nitrogen. Okay, but it's going to pick it up a little bit more now in the next few chapters. We're going to talk about the oxygen transformations and then follow it with the nitrogen transformations. Because as you know, N, O, and F are the most electronegative atoms on the periodic table. So they really like, right, to have those electrons. So they often appear as those ion-containing nucleophiles. So this is something to consider. So O and N, right? F is another beast altogether, and we don't see it as much in organic chemistry. But so when we're talking about nitrogen, we're talking ammonia, right? NH3, and then the organic analogs of that. So if you substitute one R, you get a primary, right? Okay, or if you can substitute it with an aromatic, one of those H's, then again, primary but aromatic amines. So these are the kinds of reactions we're looking at here. And the product is called an imine, also known as a Schiff base. So you may see it, you know, those two names associated with this reaction. And what that looks like is what I highlighted here in the red box. So it's a carbon double bonded to a nitrogen. So remember that a carbon triple bonded to a nitrogen is a cyanide. We've seen this as an ion. Okay, but here is a double bond. So C double bonded to an N, and then of course there's another carbon chain, right? Carbons on both sides. So this is called the Schiff base. That's how I learned it, but now the books have started calling it imine. So you might see both of these on there. So you see here that if you take, right, again, a carbonyl, this is an aldehyde. Okay, you react it with a primary, so this nitrogen is attached to one carbon, so it's primary, right? But this is the aromatic, so it's called an aniline. Then what you get is a double bond, so the nucleophile is nitrogen, attacks, opens, right? Okay, and then we'll see how we get rid of the oxygen in the next step. But it's actually just a two-step reaction, so it's a pretty, you know, straightforward mechanism. Yes, sir?
Is it more stable with the cyclohexene, or I mean the
with the benzene?
Yeah, with the
yeah. So
aromatic.
this is definitely more stable than when it's aliphatic, meaning just in a chain,
Okay.
because of the double bonds. So that's one example, and then down here is with a ketone, but same thing, right? Using the nitrogen, and in this case is ammonia. Nitrogen attacks, this opens, right? So that's really the base of the reaction, and then you get the imine plus water, right? And where's the water coming from, right? The O, and then you have to get rid of the hydrogens as well. So that's where the water's coming in. So let's see how this happens. So it's a two-step, okay? So you get the carbonyl attack, like I mentioned. So the nitrogen is your nucleophile. It attacks the carbon, the carbonyl, right? The double bond opens, that pi bond. And so what you get is this initial bond here. And then notice that another nitrogen, so just additional, right, nitrogen here, comes in. It's a base also, so it's going to come and remove the hydrogen. And when it does, then it leads to this. So you're left with the lone pair, right? And then you see that the oxygen, again, picks up the hydrogen. And this is kind of, they've done a few errors on this one, but down here is wrong, but here is correct. So the oxygen picks up, right, and now you have your alcohol, right? So it's an alcohol, and then the nitrogen, right? So that's usually what we would think the product would be. Would you agree? You attack the carbon, right? The pi bond opens, and then you end up with an alcohol, right? That's all happening in that first step. Would you agree? So this is how we've been looking at these reactions. But we know that's not the product, and the reason is because, again, you have that lone pair, right, which is not shown here, but the lone pair is there. So that lone pair can come in and bind here as a double bond, make the pi bond, which means that the OH will leave. And this should be OH here, that's where the error is. So this is this one that left should be over here. So substitute, I don't know why H ended up here, but this should be an O. Does that make sense? This is this guy over here, this ion, when it leaves. Because notice when you make the pi bond, nitrogen now has one too many bonds. It has 4 and it wants 3. So that hydroxide ion, so please correct that, that should be an O, comes in and removes this hydrogen, right? And now you have your water plus your shift base. That makes sense? So in the first step, right, that's what we usually see as the product, right, with the nucleophile attacking, makes an alcohol, right? But in the second step, you're able to lose water. And when you do, you form a double bond between the carbon and the nitrogen. And that's what we call, right, the product of this reaction, the shift base. Yes, sir?
So you're always going to need 2 moles of...
You need access. So basically your nucleophile, there's going to be more of that than you need so that it can also act as a base over here.
Why is it 6 steps in the books? Why
6 steps in the book.
Yeah.
Maybe they separated all these.
Yeah, I think so.
Maybe that's what they did. But this is all just an exchange. That's why these aren't really new intermediates. They're all kind of, associated in equilibrium with each other. So it's really all happening in that first step. And then the bottom, you lose the water. That makes sense, how we end up with that double bond between the carbon and the nitrogen by losing the water. That makes sense? Okay. All right, so then what do we do once we have these amines, right, the shift base? What can we do? So again, this is the reaction. So the ketone, cyclohexanone, reacting with cyclohexylamine, right, primary amine. So you're going to, again, attack, open, right? You're going to lose the water, right? And then you get your product, the amine here. Okay, well then you can do a reduction, right? So this is just that catalytic reduction, hydrogen with a catalyst, right? Platinum, palladium, nickel, you name it. There's a number of different catalysts that you can use for that reaction. And that's going to reduce the double bond to a single bond, right? Reduction is adding hydrogen. So that's what I'm doing here in order to go from a double bond to a single bond. And that's, again, a way, right? Why would we use this? Because it is a little bit difficult to make secondary amines. So primary amines are easy to find and we can use them as reagents, but making the secondary amine is a little more complex. So by having the amine and doing a simple reduction, we get those harder to make secondary amines. So that's the value of this initial step. Okay, now what about if I take a secondary amine and react with the ketone? So I can do that. And now the product is called enamines. So En, right? Remember, En means a double bond between 2 carbons, right? It's an alkene. That infix, right, A-N, E-N, Y-N, right, single, double, triple bonds. Does that make sense? So it's a double bond, carbon-carbon double bond next to the nitrogen. So now the double bond is not between the carbon and the nitrogen, agreed? It's next to, right, adjacent to the nitrogen. So these are different products. These are not shift bases, okay, they're enamines. And again, what are you going to do, right? You're going to attack here, open this up, right? Okay, and then again, you're going to have a transformation here in order to get the double bond. And this one is going to be followed by dehydration, acid-catalyzed dehydration. But we're going to leave this one for chapter 19. So this chapter 19 is enolates and enamines, so we're going to talk more about that. But it is the same process, right? The attack, nucleophilic, right, opens up and you form the tetrahedral. And then you're going to lose a water, right, dehydration. So same process, but we're going to end up, right, losing of the adjacent carbon. Rather than losing it between carbon and nitrogen, we're going to lose between carbon and carbon. That's an elimination, right? Does that make sense? What I'm saying? Sure. Whatever you say. That's what I don't like to hear. So you would agree that the product of this reaction, that first step, which we just saw, would be this, right?
Yes.
Right? And so we just saw a process where I can eliminate, right? If I have an additional hydrogen here, I can eliminate water like this, right? But that would give you a double bond between carbon and nitrogen. Agreed? So where am I going to lose my water in this reaction?
From your OH in one of
Right?
the
Because
opposite
there
groups.
is no hydrogen here. What's attached to this one is a, oh, I didn't draw it correctly. I'm sorry about that. But this doesn't have a hydrogen, right? It's a ring. So I don't have a hydrogen here anymore, right? So what's going to happen is I'm going to have to take a hydrogen from here. So my elimination is going to be over here, right? Get rid of these two and my double bond is now here. Does that make sense? What the difference is between a primary and secondary? The primary has one H, which gets removed in that first step. This one has two H's, right? So I have one to get rid of as part of my water, but I don't have that when I start with a secondary amine. Does that make sense?
So with secondaries you have one H and primaries you have two H's.
Yes, so a primary is NH2, that's primary. A secondary is an NH. There's only one hydrogen versus two hydrogens. The first hydrogen gets lost in that first step. If I go back here again, right? See, it gets removed up here. But since this is primary, there's still another hydrogen, see? So it can be removed down here, or I'm sorry, over here, right? This step. But there's not going to be two hydrogens, only one hydrogen, right? Does that make sense? Yay?
Yeah.
It's the number of hydrogens here that are really precluding you from making the enenes, right? The shift base versus the enamines, which is the adjacent. Does that make sense?
So the point of these is to be able to form a secondary
Well, you're trying to form a bond between the carbon and the nitrogen, but when you do it with a primary amine, then you will get that double bond, which can then be transformed into the secondary amines. But this is already starting with a secondary amine and giving you that enamine, which we're going to see we can do additional. This can be transformed into an ion, just like the enolate. So we have a whole chapter on that, which is chapter 19. So we're going to be able to be very useful, but we just don't want to get into that right now because it has its own chapter. So we don't want to confuse
sneak
things.
peek to get
This
us
is a
ready
sneak
for-
peek, yeah. So just so you know, yes, you can start with a primary, or you can start with a secondary amine. Right? That's really what we're trying to get at here. But then we're going to be able to do a lot with this in chapter 19. We're just not quite there yet. But I want you to be able to understand this concept. The hydrogen is necessary to make water. Would you agree? Yes. So the hydrogen can come from the carbon or it can come from the nitrogen. But in a secondary amine, I don't have enough hydrogens in order to make the double bond happen over here. Right? That's what I want you to be able to understand. Yeah, right now.
But could that happen at any of the carbons?
Only the carbons adjacent, so it could have been down here too, right? There's hydrogens over here. So you could argue that, yeah, it can either be here or here, but this is too far away. It has to be, right, the carbons have to be next to each other in order to form a double bond. But it cannot go this way with a secondary amine. That's the key. It can go this way or that way. That makes sense? All right, so then related here also are hydrazines. So a hydrazine is similar, but it's not a carbon, right, attached to nitrogen. It's nitrogen attached to a nitrogen. So that's called a hydrazine, right? So it's not nitrogen attached to carbon. That's an amine, but it's nitrogen attached to nitrogen, right? Does that make sense? So that's a hydrazine. You also get that double bond between the carbon and the nitrogen, but it's not called a shift base because there's not carbons over on that side. There's nitrogen, so this is called a hydrazone. So just a bit different there. And there's different reagents that can be used. So hydrazine is nitrogen, nitrogen, but you can also use nitrogen oxygen, hydroxylamine. You can use the nitrogen attached to another nitrogen, but then with a benzene. So again, that's phenylhydrazine. Does that make sense? Nitrogen, nitrogen, and then you have this dinitrophenyl, right? Nitrogen, nitrogen, and then this amide. So this is a carbazide, semi-carbazide. So different reagents that can be used. But in the end, there's going to be a double bond formed here, right? Double bond, double bond, double bond, double bond, right? Nothing is going to happen to the remainder of the molecule. Okay, so that's the nitrogen reagents, and again, we'll talk more about these in chapter 19. But just want you to know they are great nucleophiles. So you will, see a lot of this coming up. All right, so now we want to talk about the carbon next to the carbonyl. So the carbonyl, right, we've been attacking it over and over again. Now I want us to think about the carbons next to the carbonyl. So nothing is going to happen to the carbonyl in this section. We're going to talk about the carbon next to, which we call the alpha position. Remember alpha, right? Or right next to, and then next to that is beta, right? And so on and so forth. And so this is alpha to the carbonyl. So is this. Would you agree? And if they have hydrogens attached to them, which both of these carbons do, we call them alpha hydrogens. And these alpha hydrogens are acidic. So look at the pKa. It's about 20. That's not great. But we know that the alkyne, we can remove hydrogen here, right, to make an alkyne ion, carbanion, at 25. So 20 is decent. So you can consider these alpha hydrogens to be acidic. Not hugely acidic, but enough to do reactions at this position. Okay, so now we're not talking about the carbonyl, but the carbons next to. Okay, does that make sense? Okay, so those are considered to be acidic. So what can happen then, right? Well, I can imagine that I would remove one of these hydrogens by a base, right? Because this is an acid, it's going to react with the base. Okay, so the base comes in, removes the hydrogen, so those electrons go back on the carbon. Right, so you're kind of seeing where we're going with this, right? We now form a carbanion. And because it's next to the carbonyl, it's going to be stabilized by the resonance structure, right? Moving these over here and then putting the negative charge on the oxygen, which is where the negative charge is most comfortable, right? Oxygen likes electrons. Does that make sense? So because you can do this position is a potential site for reactions as well. Does that make sense? So the alpha hydrogens are acidic, okay, which means we can do reactions here. And so what kind of reactions are we kind of leading to? Again, this is going to be talked about more in chapter 19, okay, but basically, right, you have the keto form, and we've already talked about that you can, if you remove this hydrogen, right, you then end up with your carbanion, then that carbanion, we can shift things around to put the charge here on the oxygen. And you can imagine that if I had an acid on this end as well, that H would go to form the alcohol. And this is what we call the enol form, the double bond adjacent to the alcohol, which we've already talked about. And remember that the keto form predominates, which means that when you're drawing the ion, the enolate ion, this is the reactive form. And again, chapter 19 is called enolates and enamines. So we're going to, again, talk more about reactions for that at that point. Yeah.
So it's basically just a shift of electrons.
Yeah, this part, so you're removing a hydrogen starting out. That's what starts out this process. But then, yes, as a intermediate here, as an ion, you're just moving the bonds. And remember, oxygen would prefer to have a negative charge than a carbon, right? Because oxygen is more electronegative. So consider that. Yeah, you there?
Well, there's only happen with carbonyl.
It does not. No, because see here, this is available too. So it can happen over here or it can happen over here. Either side. It's just the example is giving you both CH3s. But if there was CH2, you know, CH3, it would still happen on the other side as well. So any alpha position is going to end up in this situation. Yep.
That's what I was going to ask. So any alpha position will, even if the chain is longer.
Yes.
Okay.
Yep. Which means you usually don't get a single product for these reactions. You get multiple products.
You could have the double bond on either one of the two.
You are going to be able to form right on one side or on the other side. Of course, this is symmetrical, so it's just going to give you one product. But if you had one side that was longer, you would get a product here and a product here. Does that make sense? So you usually get multiple products of these reactions. But again, in chapter 19, we're going to see how do we curtail that? How do we make one side more favorable over the other? We don't have that knowledge yet, but we will in chapter 19. But for now, you just want you to, again, consider that you can remove the hydrogen from the alpha carbon, forming these ions. That's what I need you to know now, just as a starting point. Okay, and again, this is just showing you the mechanism for that. So this can be, this is showing as acid catalyzed. So the oxygen, is going to pick up the hydrogen, open it up, and then you have it, with that, what's the word? The oxide ion here. So you have this, which then is susceptible to the base. So this is a reversible process, right? And so that can go on to the second step, and then this is vulnerable for the hydrogen to be removed. You shift your electrons here, and then you end up with your enol form. So that's if you have a base, acid. Can you do this with a base? Yeah, I just saw it previously, right? Here you have a base, right? It removes the hydrogen, and you end up with the enol form. So you can do it in either acid or base. So those are the enols, and again, enols themselves open up a whole bunch of other reactions. So we'll keep that for 19. Okay, so that's the alpha position. So now back to the keto position, and let's talk about oxidation. So remember that when we talked about oxidation of aldehydes, we can use Jones reagent to make the carboxylic acid. So we've already learned that, but we said Jones reagent does not oxidize the ketone any further. Okay? That doesn't mean ketones cannot undergo oxidation. They can. Okay? But you'll need higher temperatures, and you'll need concentrated acid or bases. So they do not happen under the conditions we've seen before of Jones reagent or chromic acid, PCC, none of those. So usually you're going to need, so make sure I say it right, nitric acid. I said it wrong on Friday. Dr. Johnson corrected me, so now I'm going to try to make sure I say it right.
Your way's better.
My way's better? It's nitric? I said nitric and she corrected. So I said it correctly today though, right? Nitric acid. Nitric acid.
If you really wanna
Stick with
if you
nitrogen.
really
It
wanna
was
have
my-
fun with
my
her,
impression.
Just say nitrogen.
say wind boat instead of massing boat.
No, no, say mass.
Massing boat. instead of-
Massing boat, that's what
Massing.
she likes, or she likes weighing boat?
Like massive.
It's a
Massing
mass.
boat,
It's a
okay.
mass.
Let's say weighing boat and just have some fun.
Just
We
see
used to
what
do
she
that
says.
in her.
Well, I didn't want to say it correctly, so my students learn it correct, so nitric acid.
Nitrogen.
So, nitrogen? Yeah, I should remember that. See, trigonal and trigonal, like, those make my head also, I can't keep those straight either. But you need, again, that acid, right, and then you need high temperatures for these reactions. And what happens is that if you imagine that the keto form, right, can be transformed, we just saw that, into the enol form, right, that can happen. Okay, then you can see that the double bond could break, like we saw with the HiO4, remember that reaction? And then it breaks at the double bond to form two carboxylic acid groups. So basically it's opening here, so you have 1, 2, 3, 4, 5, 6 carbons, right? 1, 2, 3, 4, 5, 6 carbons. And at each of the ends, you're going to get the carboxylic acid. Does that make sense? So this is what happens when you oxidize a ketone. You form, again, you break at that double bond enol, right? And then you form the two carboxylic acids as a product.
But it's only in
So-
cycloketones though, right?
No, it's in any ketone. So if it was a linear ketone, what would happen? So what if my ketone was like this?
I don't know.
I don't know. What would happen, right? It could, right, form that, right? And then this is the double bond that would break, right? So my product would be 1, 2, 3, 4, right? And, right, 1, 2. Does that make sense? Is that the only product? No, because my enol, you go the other way. There's no preference. They're both secondary, right? So now I could have a product over here that is 1, 2, 3, and 1, 2, 3. So this gives me the same product. Would you agree? Which one too many? 2 of these, right?
Right.
So this can happen. This example is cyclic, but it does not have to be cyclic. It just has to be a ketone. Does that make sense? What Diego asked. So we had not seen ketones being oxidized, okay, but now we have the reaction. So you should consider this, okay, a possible mechanism. So that's oxidation. And again, we already know oxidation for aldehydes, right? So that's Jones reagent, and it oxidizes to the carboxylic acid. We already have that one. So what about reduction? Okay, so we can take aldehydes and reduce them to primary alcohols, because remember the aldehyde, the double bond H, right? That is at the end of the chain. So it's always going to give you primary alcohols. The ketones are in the middle of the chain, so you're going to get secondary alcohols. Now, you don't stop always at the alcohols in the reduction. You can sometimes, under certain conditions, go all the way to the alkane. Get rid of the alcohol altogether. So you can see the aldehyde here can be converted, reduced to a CH3, and you can reduce the ketone to a CH2. So we'll see which reagents are going to be able to do, okay, alcohols versus alkanes. Does that make sense? So reduction, lots of different opportunities here for reduction. So the two most common reagents for this are the ones that produce the hydride ion, and those are the lithium aluminum tetrahydride and the sodium borotetrahydride. So they're NADH4 or LiAlH4. And again, the whole point here is that both of these can release a hydrogen, right, as a hydride, not as a proton, right, H+, but as an H-. And that's really the key. That's a powerful nucleophile. So with NADH4, the This is going to be done under protic solvents, so polar protic methanol as an example here. And what you get is, because you have 4 hydrogens, you can actually oxidize 4 of the aldehydes or ketones. Okay, so you get 4 alcohols as your product. Does that make sense? So 4 hydrogens means that you can reduce 4 moles of your aldehyde or ketone. So this ghost product is alcohol. And again, the way this reaction works is that the hydride, the hydrogen with the electrons, attacks like a nucleophile. The double bond O opens, right? It forms an initial salt, right? And here's your H, your hydride as a nucleophile added on to your tetrahedrocarbon. And then, of course, you add right here water in order to get the hydrogen, so you finish your alcohol. Does that make sense? So the H came from your reduction agent, the sodium boryl tetrahydride here. Does that make sense? So the hydride is acting like a nucleophile, so you add an H this way. Now what about the lithium aluminum tetrahydride? This is very reactive with water or any actually protic solvent, polar protic solvent. So what we have to do is do it in a ether as a solvent. So ether is not, it's aprotic, so it's not going to cause a reaction with the lithium aluminum tetrahydride. So that's really the only difference, right? So you take 4 hydrogens, so you can, right, reduce 4 of your aldehydes and ketones, and you make the alcohol as the product. And THF is another good solvent for this. So tetrahydrofuran, remember that's the 6-membered ring with the oxygen. So that's also aprotic, so it works well in this reaction. And so these are usually also can be done with your catalytic reduction. So hydrogen in the presence of the catalyst, metal catalyst, and it's platinum here. And then you have, right, 25 degrees and 2 atmospheres. But sometimes, depending on what your initial aldehyde or ketone is, you have to heat it up. It can go as high as 100 degrees. Okay? And you may also have to tinker with the pressure. So usually we say 2 atmospheres, but you may have to go all the way up to 5, again, in order to get this reaction to work. Okay? So they're a little bit harder to do, but the product is still the alcohol. Does that make sense? So now what happens though if we take, right, this reagent, right, the catalytic reduction, we've also saw this for alkenes, didn't we? That's a reduction agent for double bonds, carbon-carbon double bonds. So would you agree with me that if I had this reagent, I would reduce both the double bond to a single bond, and I would reduce my carbonyl to an alcohol, right? Does that make sense? So if I use this reagent, right, 2 moles, 1 mole would reduce here, and the other mole would reduce here. So my product would look like this. No more double bond, no more carbonyl. Do you agree? Right? It works for both. So we say this is right, or not selective. Does that make sense? It will reduce everything. Now what if I don't want to reduce everything? Let's say I just want to reduce my carbonyl only, right? So then I can do what it's called selective reduction, and I use lithium aluminum tetrahydride. That does not reduce the double bond. It is not an alkene reduction agent. Does that make sense? So it's only going to reduce my carbonyl to an alcohol, right? The double bond's still there.
And is that because of, why is that?
Because the lithium aluminum tetrahydride, that hydride is a nucleophile. And so the nucleophile only attacks the carbonyl, right? These are electrophilic additions. So nucleophiles don't attack double bonds, right? Remember, those are called electrophilic additions, the ones that the alkenes undergo. But the hydride is a nucleophile, so it's only going to attack the carbonyl. Now what if I want the opposite? What if I want to only reduce the double bond, right? And keep the carbonyl the same, intact. Okay, well I can use another reagent, so it's called RH, right? And it is rhodium. It's a metal on the periodic table. 45. Okay? So if you use this particular catalyst, you now only reduce the double bond. You do not reduce the carbonyl. Does that make sense? So these are called selective reductions. So be aware that you need to pick the right reagent depending on what you want to do. If you don't care, if you don't mind reducing everything, if the product you want is the butanol, then you're good. But sometimes you do want the double bond, right, to stay, and sometimes you may want the carbonyl to stay. So you want to pick what you want. Yeah.
How come rhodium does the exact opposite and just focuses on?
Yeah, so rhodium is going to, it's not going to add, it doesn't have the hydride as the nucleophile. It's going to have hydrogen gas also, or hydrogen like this, H2 gas. And so it's only going to work on the double bond. So the only ones that work on the carbonyls usually are, you want to consider that hydride as your nucleophilic addition product. So that's not available here. So you do want to consider, this is called selective reduction. So, does that make sense? All right, now what if I want to reduce all the way down to the alkane? I don't want it to be an alcohol, right? I just want it to go all the way to the CH2. Right? What reagent would I use then? Well, this is called the Clemson, not Clemson, but Clemson reduction. So this is with zinc. It's a zinc-mercury couple, okay, in the presence of an acid, so HCl is present there. Okay, and what's going to happen again is the carbonyl doesn't go to the alcohol like we just saw. It goes all the way to the CH2, to the alkane. So that's another consideration you want to have. Okay, do you want the alcohol? If you do, this is not product with the reagent for you. So this goes all the way to the alkane. All right, and here's another example. So if you want to do another Wolff-Kishner reduction, this is another combination of reagents. So see hydrazine, right, which we talked about previously today in the chapter. So the two nitrogens connected together. Okay, that in the presence of KOH. Okay, and diethylene glycol is just a solvent, and its reflux means what?
Under reflux.
Under reflux means what? What does that look like in lab?
The
Column. It's called a reflux.
Yeah.
Right, a condenser. But what does that mean? It's heated, right?
Yeah.
So the solvent gets hot, it gets to the column, and what happens is cold, and it comes back down. So you never lose the solvent, right? If you just had the bottle open heating, the solvent would all become gas and never come back, and it would dry out, right? We cannot let it dry out. That's what reflux is about. So you've probably done it in lab by now. So since I'm not teaching the lab, I cannot assure, but I think you have. But this is the, again, conditions that would lead you from the carbonyl to the alkane, no alcohol.
I feel like the other. I feel like
The other one
the other reagent's more simple.
simpler, but zinc mercury is nasty. That's the problem, right? This combination.
It just smells better.
No, it's bad for you.
Oh,
It's very
bad.
toxic. So hydrazine is more commonly just common to lab use because it's not toxic. I mean, everything in moderation, right? I mean, you don't want to be too exposed to anything, but and it also, it's cost, right? It's, if you have the conditions like refluxing and things like that, you don't need to do that here. So, I mean, there's different considerations to why use one over the other, but both will give you the alkane though, so you can choose. Okay? So those are reduction reactions. Does that make sense? Does everybody understand selective reduction, when to use it? Right? You have to select if you don't want everything to be reduced.
Can we skip though?
So, is that not there?
Can we skip to,
Did I skip something?
yeah, we have racemization first.
Yeah, no, go ahead. Just cross those out. Those 2 slides on page, whatever that is.
Does it care about those
115.
slides?
I got rid of those. You know, I've been trying to update, but I haven't updated, I guess, your book. So that's it for reduction. So the last thing we're going to talk about is this alpha position again. And now a reaction that we can actually do there, which is called alpha halogenation. So again, halogens, right, bromine, chlorine. And so again, if you take the bromine or the chlorine, it's not going to act in this way as a nucleophile. Okay, it's actually going to act at the carbon next to. Right? Does that make sense? So this is going to be at the alpha position, and what you get is the halogenation. You add the halogen to the alpha carbon. So this is really substitution, right? You're substituting the bromine for a hydrogen. And this can be done in either acid or base. So this is an acid, this is acetic acid. Okay, and so this would look like this, right? If you had an acid, you would tautomerize to your enol form, right? So you would have the hydrogen here. They're not showing it, but you would add the hydrogen here, tautomerize, so that that hydrogen is now, right, that OH that came from the acid. Okay, and then in this step, the double bond attacks the bromine, okay, and then you do this at the expense of forming the double bond between the oxygen and the carbon. So you can see that you form that, but that's an ion, so you have to have the proton transfer to finish out this process. So that's acid catalyzed. What would happen if this was base catalyzed? Well, if it's base catalyzed, then I deprotonate first. So I'm going to remove the hydrogen from here, right? The carbon, remember that's an acidic hydrogen. Okay, and then again you'll go, right? You'll form this double bond, the enol form, and that goes into the second step. But again, the double bond will form between the carbon and the oxygen, and the double bond will pick up the bromine. And you get, again, the product with the alpha halogen, right, at the alpha position.
The base and the acid are basically the same, except the first step is a little bit different.
Yeah, in an acid, it's going to donate the proton. So that's a protonation. This is a protonation reaction. You're adding a proton. In the base, you're removing the hydrogen, so this is a deprotonation reaction. So the first step is different, right?
What the product is that?
Is the product the same?
The product is the same.
What's the difference between this and NBS?
This and NBS.
Because you're just adding.
Well, NBS is for a double bond, not an aldehyde or ketone.
Okay.
So it's a C double bond C, not a C double bond O. So NBS, these are not radical mechanisms. NBS, I mean, the whole purpose is that it's going to initiate a radical mechanism. These are not, right? These are still doing substitution addition reactions. And so just a few things to consider is that with the acid catalyzed, the introduction of the second halogen, so let's say that I wanted to replace, well, these have carbons, but let's say I had additional hydrogens, like there's a CH3 over here, right? So I'm adding just one bromine, but let's say I want to add another bromine. There's still 2 hydrogens here, would you agree? Okay. Well, when you're trying to do that, the acid catalyzed, that second halogenation is slower than the first. And the reason is because you now have a halogen which is electron withdrawing. So remember that when you have electron withdrawing groups, you actually decrease the basicity of your carbonyl. You're pooling electrons, right? That's what electron withdrawing means. So the base catalyzed, if you're looking to do additional halogenations at that alpha position, it's going to be more rapid because it's going to do the opposite. It's going to increase the acidity. So If it decreases the basicity, it means it becomes a better acid, right? So depending on what you want to do again, if you want to just replace one hydrogen, you're good with an acid. But if you want to replace multiple hydrogens, you should use the base. And you asked me which one was better, and I said, you know, we would eventually figure that out. Well, more evidence that base catalyzed might be the best way to go.